Welcome to videos on clean integrated circuits. So this is part 6 of DAC, that is digital to analog converters. So in the previous video we were discussing about capacitor potential divider. So we have considered a capacitor C1, C2 and C3, C4, C5 connected in this fashion. So we are supposed to estimate the voltage at Vx, so where the voltage given to the network as V1. So we can rewrite this by this equivalent circuit because C1, C2 are parallel. We can write it as a single capacitor. Similarly, the bottom capacitor has C2, C3, C4, C5. So naturally, if you name this as Cx, this is Cy. So the voltage Vx is given by the input voltage V1 multiplied by the capacitance offered by the impedance offered by this Cy, which is C3, C4, C3 plus C4 plus C5 divided by the overall impedance of the network. So which will be reduced to Cx divided by Cx plus Cy, where Cx is given by C1 plus C2 and X plus Cy is given by the sum of all the capacitors C1, C2, C3, C4, C5. So this is the sum of all the capacitors. What we are trying to establish here is that suppose if you have two capacitors in series, the voltage at this series at this middle of the capacitor is given by C1 divided by C1 plus C2. Now if you have something like this, now the capacitance, the voltage Vx is given by V1 multiplied by C1 C2 divided by the sum of all the capacitors. Overall, the conclusion here is that if you want to find the voltage Vx, it is V1 multiplied the capacitors connected to V1 and the total capacitors. Now you can see the capacitors C1, C2 are connected to voltage source V1, and in the denominator we have all the capacitors that are there in the network. Meaning to say the Vx of this network is V1 multiplied by the capacitors connected to V1, that is C1 plus C2, and the overall capacitance of the network, that is C1 plus C2 plus C3 plus C4 plus C5. So using this concept, we try to develop a DAC network which we call it as weighted C Dac. Now here you can see, so we have capacitor C by 2, C by 4, and C divided by 2 to the power of n minus 1, and there is one more capacitor which is connected in this fashion, and we have switches SW0, SW1, SW2, and it is keep on going like this. And this is a voltage follower, and we have a V reference voltage. Let us try to understand the working of this circuit. So initially all the switches are open, only switch SW0 is connected to this ground, meaning to say when all the switches are open, when only SW0 is switched on, when it is connected to ground, all the capacitors will be discharged to 0. So whatever charges that are there in the capacitors will be discharged to 0. Then once that is like initial condition, making all the capacitor discharge to 0, then you open the SW0. So switch 0 is opened, and depending on the binary input, you are supposed to make it as 1. It's like, okay, MSB bit 1, so this is the next bit, this is the next bit. If you want to have it as 1, you connect it to VCC. If you want to have this bit as 0, connect it to ground. You can see one is connected to V reference, the other point is connected to ground. If you want to connect it to 1, you have to connect it to this point. If you want to have this bit to be 0, it's connected here. So it will be either switch between 0 and 1. Here also it is 0 and 1. So all the bits are switching between 0 and 1 depending on the requirement, and only SWC switch 0 is initially made to ground so that you can discharge all the charges, and during the evaluation purpose, that is during getting the V0 corresponding to the binary input, we open this switch. When we are opening this, so this will not be effective. During the required output voltage, we'll be making either SW1 to all other switches except SW0, so they will be either in 0 condition or 1 condition. Let us take up an example and try to find out how does the circuit works. Now this is what the circuit what we have. using the elementary capacitor divider principle, that what we studied earlier. So we can readily say that the voltage V0 is given by V reference multiplied by CR divided by CT. So what is this CR? Where CR represents the sum of all the capacitances connected to V reference, and CT represents the total capacitance of the array. Meaning to say, suppose if you are connecting any capacitor to V reference, so that CR is actually the sum of all the capacitances connected to V reference, and CT is the capacitance, that is all the capacitance of the network. So this is exactly resembles our expression what we have written here. This Vx is nothing but this V0, and V1 is nothing but V reference, and this capacitors connected to V1 is nothing but all the capacitors connected to V reference divided by the total capacitors. So that's what is the conclusion here, the V0. So here you can see this V0 is same as this point, because this is a voltage follower. Whatever voltage appears here will be available here, because this is just acting like a buffer circuit. So voltage at this point, which is our Vx in the earlier slides, is equal to V reference multiplied by CR divided by CT, where CR is the capacitance is connected to reference, CT is the total resistance. Now we can write, so by considering the values of the capacitors that are there connected in this fashion, CR can be written as, because CR is the capacitor that will be connected to the V reference, CR can be written as B1 into C. So this is the switch B1. If B1 is connected to 1, so this capacitor will be connected to V reference. Plus, now depending on the value of B1, B2, B3, the capacitor, that particular capacitor will be connected to V reference. So you can see now here, if B1 is 1, so this C capacitor is connected to V reference. If B2 is 1, C by 2 is connected to that. And if B3 is 1, C by 4 is connected. Now you can see it is its weight is keep on reducing at the rate of 2 power n. So this is C by 2, and it is interesting to see the last capacitor will be having a no switch, so this is permanently connected to ground. See here, so this capacitance value is C by 2 to the power of n minus 1. It is necessary to observe that the summation of all the capacitors will always turn out to be 2C. So whether you have any number of bits, whether it is 2 bit, 3 bit, n bit, the sum of all the capacitor, as you can see here, it is C by 2, C by 4, C by 8. Assume that you have only, we'll just take up an example in the next case and try to identify how does this will work. So V0 can be represented as V reference into B1 into 2 power n minus, sorry, 2 power minus 1 plus B2 into 2 power minus 2. This is the usual expression of our DAC. Now, by having the capacitors of this value, that is C by 2, C by 4, C by 8, we can realize the weight of the binary input will going to represent the output voltage. So output expression is given by this equation. Let us take up a 3-bit weighted C DAC. Now since it is only 3-bit, we have considered, now we have a switch for resetting the capacitances. Now we have one capacitor which is there at the LSB part, so which is always connected to ground. Here you can see the value of this capacitance is always equal to the LSB value. The MSB is always C. This is C by 2. Now this is C by 2 square. This is only 3 bits. Since we have only 3 bits, it is C divided by 2 power n minus 1. Since it is 3 bit, n minus 1 is 2. So assume that we want to estimate the value of V0 for B1, B2, B3 as 100. As you can see, it is 100. So only this is connected to 1. So all others are 0. You can see now this is 1. This position of the switch is 1. This is 0. This is 0 because it is grounded. It is 1 because it is connected to V reference. You can see now this is B1 MSB, B2 B3, B3 is LSB, and we have one more capacitor which is exactly having the value that of the LSB bit. So you can see it is C by 2 power 4, which is actually C by 4 here. This is C by 2, this is C. So now you can see only this is connected to 1. These two are 0, 0. We can actually find out what is the effective equivalent circuit what you have here. Now you can see this is the combination what we have. If you can see it over here, this is V reference. To V reference we have only this capacitor C connected. You can see only this C is connected, and the other three capacitors you can see this is C by 2 and this is C by 4, another C by 4. The voltage at this point V plus is having only one capacitor which is connected to V reference. The other three capacitors are connected to ground. So from the equation whatever we had there in the earlier case, the V naught is given by V reference multiplied by CR divided by CT. So V reference in this case is this V reference, and the capacitor that is connected to V reference is only C. The other three capacitors are of course this is like CR, the capacitor is connected to C reference, sorry, the voltage reference, and the total capacitance. Total capacitance is C plus C by 2 plus C by 4 plus C by 4, as it was said that always the total capacitance is equal to 2C. Now you can see this is 2C, the denominator. The numerator we have only capacitor C is connected. We end up with V naught as only V reference by 2. We know that always the contribution of the MSB is half of the reference voltage. So since it is only 100, we have the output voltage as V reference by 2, which is V plus here. Since it's the voltage follower, whatever is the voltage at V plus, in this particular case it is V reference by 2. The same thing will be available at V naught. So we have V naught is equal to V reference by 2, which we can certainly get it using this expression also, where V naught is given by V reference into B1 into 2 power minus 1 plus B2 into 2 power minus 2 plus B3 into 2 power minus 3. See, now this is only since bit B1 is 1, so this is 1 0 0, so these two bits are 0 0, so we have only 2 power minus 1, so V reference into 2 power minus 1 is nothing but V reference by 2. So this way we can get the output voltage as V reference by 2, which is corresponding to B1. Assume that I'm making only B3 as 1 and these two are 0 0. When B3 is 1, so we have this CR as C by 4. So this will be C by 4 and this will be 2C. So you have C by 4 divided by 2C, which happens to be CC will cancel out. You want to have it as 1 by 8, because if you have only B3 as 1, so this will become C by 4, because this capacitor is connected to V reference. The other three capacitors are connected, all other total capacitance of the network is 2C. When we have C by 4 by 2C, so that will become 1 over 8. So 1 over 8 into V reference is actually the output voltage at this point, which is the LSB of the output voltage. So likewise, depending on the combination of the input voltage we have it here, the output voltage is exactly this is contributing half, this is contributing 1 by 8, this is contributing 1 by 4. If the combination of the input changes, the output voltage also changes as per the expression. So it is very important to have uh, three capacitors of this value, that is C by 2, C by 4, and there is one more capacitance of the same value as that of the LSB is always permanently grounded to this point, because we need to have the total capacitance of the network has to be always 2C. Let us have a look at what is the advantage of this weighted C capacitance. Since MOS capacitance ratios are easily controllable up to a ratio of 0.1 percentage accuracy, the weighted capacitance capacitor scheme is suitable up to n close to 10, so less than or equal to 10. In the previous case, you might have seen that weighted R, since the realization of resistance R is very cumbersome in to realize it on ICs, it was restricted to only 6 bits. Now we can go up to 10 bits. As the weight of the resistor of DAC, the main drawback of this system is exponential. In case of weighted the resistors, we saw that the the resistance values keep on increasing exponentially. Here also we have the same problem here. So the spread of the capacitance is exponentially varying, as you can see now. in the for a 3-bit capacitance also, for a 3-bit weighted capacitor weighted DAC,